Missing anybody, I'm gonna go ahead and take the homework and put rubber bands around it. How was today's homework? Is it easy? It wasn't easy? Where's James? Am I like the only professor that tries to start on time?
Yes. Yeah.
Really?
Actually, yeah. Dr. Stevens starts like 10 minutes late. And I don't know.
I like how precise your edges are there, David. All right. Any questions? So today we're going to talk about voltage references. So if you took 421 from me last fall, you remember how we had a band gap and you had to use it for your projects? If everything goes well today, you will understand how to design a band gap. We will see. We will see. All right. So a couple of things. Refresh my memory. Did we talk about temperature coefficient of resistors, for example?
No.
All right, I'm going to go through it real quick. So generally, if you plot a resistor's value versus temperature, generally it goes up. And, you know, that's what's when you use a resistor to sense temperature, what is that called? Thermistor, yeah. So you can use resistors to sense the temperature, but a lot of times you don't want things to change with temperature. So the way this curve is described as the temperature coefficient of the resistance times 1 minus or 1 plus the temperature coefficient of the resistor times T minus T0. And so at some measured temperature T0, you get R of T0. And if you plug in, whoops, I got a mistake here. If you plug in T equal T0, what does this equation reduce to? R of T0, right? Okay, so now what is the slope of this line if I take the derivative of R of T with respect to temperature? R of T0 times TCR. Everybody agree with that? In other words, TCR is equal to 1 over R of T0 times del R. I'm going to leave out the T's, del T. Does everybody follow that? So when I do calculations and I see this, I'll see this all over the place, and this is simply a number. And if the resistor's variation is linear, then this might be 0.002, for example, or 2,000 parts per million per degree C. So 2,000 or parts per million is a multiplier of 10 to the minus 6. So 2 times 10 to the third times 10 to the minus 6 is 0.002, or 2 times 10 to the minus 3. Anybody not follow this? So I'm telling you this because we're going to see these all over the place in the chapter. And these are numbers you read off of a table. They're measured. Even though it looks mathematical, you use the numbers to calculate what the temperature behavior of the device is. All right, any questions on that? Okay, so the next thing we're going to do is we're going to, how was not having class on Wednesday? It was nice.
I find myself to yeah.
All right, I don't know what to say. All right, so the next thing I'm going to do is I'm going to point out if I have a constant current I and I go into a diode and I measure the diode voltage. And I change the constant, and I change the temperature, and I plot. Oh, one other thing I should point out here before we move on. If a resistor has a positive temperature coefficient, the slope is going up. And if a resistor has a negative temperature coefficient, the slope is going down. And if you read in chapter 4, there's a discussion on how you could have positive or negative temperature coefficients for resistors, all right? So just so you see that. So now if I take this circuit here and I plot the diode voltage versus temperature, I will generally get a curve that does something like this. And the slope of this curve for a silicon diode, normal PN junction, is about minus 1.6 millivolts per degree C. So what that means is if temperature goes up and you keep a constant current through the diode, then over time what's going to happen is the diode, with variations in temperature, increase in temperature, the diode's voltage will decrease. So what was another temperature parameter that we talked about that decreased with increasing temperature? Threshold voltage. Okay? So now I'm going to do an example for you. So let's take the following circuit, which I'm going to use just the beta multiplier as an example. And I've got my nice little bias circuit here. And so before I go any further and connect anything up, what's the point of diode connecting these devices? It allows this node to go to VDD minus VSG. So as VDD goes up or VDD goes down, this node can go with it, right? This node can then be at whatever VGS is. If this was grounded, it can be VGS plus whatever's connected there. It allows these two nodes to go to different voltages while keeping the current the same in each side. So, question. Do I need to concern in the following discussion, do I need to concern myself with the temperature behavior of the mobility of the transistors and the source gate voltages of the transistors, or gate source voltages? Do I need to take that into account in this circuit? Well, let's just look at the PMOS. If the temperature changes, do I need to take that the variation in the threshold voltage or mobility influences things? No, because if it changes, it's changing the voltage, the VSG here, but it's not changing the currents. The currents are going to be defined by what's going on down here. So let's actually do this. So let's put this at ground, and then let's put our resistor here. Let's make this K times wider. So what does the K stand for? Beta multiplier. This is K times wider than this one. Looking good? So I want you to determine the temperature coefficient of this circuit. So, because this is one of my favorite quiz and test questions, let's real quickly rederive the current that flows, I. Tell me how to do that. What is it? So what's this voltage here that I have? And then isn't VGS equal to the square root of 2 ID divided by I'll just write beta, but I'll write it as Kp times W over L plus V threshold N. And the key takeaway is when you use this right here, what happens to the threshold voltages? They go away. So then I write, oh, well, VGS1 would be square root of 2 ID all over Kp times W over L minus the square root of 2 ID all over Kp times K times W over L. And that's divided by R is equal to I. We'll call it ID. Anybody agree with that? Yep. All right. And then let's not waste paper. I'm going to factor out how about I factor out the square root of ID. So or divide both sides by the square root of ID. Over here I get square root of ID. So I get square root of ID is equal to the square root of 2 over Kp times W over L times 1 minus 1 over square root of K. Looking good? Or finally, ID is equal to 2 over Kp times W over L times 1 minus 1 over square root of K squared. R squared R. Just in case there's anybody that loves math out there. All right, any questions on that? And so now our question is, how does the reference current change with temperature? So I'm going to rewrite this equation over here as ID equals 2 over R squared times Kp times W over L times 1 minus 1 over the square root of K squared. And now when I write I'm going to try to find the derivative or the change in the drain current with temperature, but before I do that, refresh my memory on what changes with temperature here in this equation. Does the K?
No.
No. Does the W and the L? No. Does the KP?
Maybe. Yes. Yes, it does.
It has the mobility in it, right? So if I go back to chapter 9 and I go look at how Kp changes with temperature, I get 1 over Kp del T is minus 1.5 over T. And what's the units of T here in this equation? Kelvin. You can't use Celsius because then it doesn't work out because it's not a difference. And a lot of them where it's like T minus T0, doesn't matter if you use Celsius or Kelvin here, it matters because you only have T. All right. What else changes? The R. Yep. So here, since I've done this a few times and I know how to explain it best, or at least I think I do, I'm going to say let X equal 2 over W over L times 1 minus 1 over the square root of K squared. Then I'm going to say ID equals R to the minus 2 times Kp to the minus 1 times X. Then I'm going to say the derivative of ID with respect to temperature is equal to X times minus 2 R to the minus 3 del R del T times Kp to the minus 1. Here's where I'm always afraid people don't know calculus. All right. Plus.
Well, it's actually minus.
Well, let's leave it plus and I'll just put here square brackets. All right, looking good? Who agrees with that? All right, so why don't we do the following? I'm going to leave this x, and I'm going to factor out a r to the minus 2. My spidey senses are tingling. I'll just leave that out. R to the minus 2. And then I'm also going to factor out a kp to the minus 1. And then I'm going to leave the first term as minus 2 times 1 over r del t. Anybody agree with that? Why? Why did I do that? Why did I write 1 over r del t first page today lecture?
Oh, because that's the, you can look that up on the table.
Yeah, it's a TEMPCO, 0.002, 2,000 parts per million. All right. And then what about the next term? Get rid of the r to the minus 2. I have a minus 1. Kp goes out, and I'm left with anybody agree with that? A what? Oh, I shouldn't have put that in there, should I? Yep. All right, so let me write this nice and clean, but I'm going to get rid of the x in here. And so I'll write del ID del t equals 2 over w over L times 1 minus 1 over the square root of k squared. And then I'm going to pull this out and write r squared and kp. And just as a sanity check for myself, so everybody got that? I pulled the 1 over r down into the denominator. And what is 2 over r squared w over L times kp, if you can read that? Times 1 minus 1 over the root. What is this right here? Yeah, it's ID. Okay? Continuing, and then that's times minus 2 times 1 over r del t minus 1 over kp del t. Anybody agree with that? So now let's write how the temperature changes with temperature, or how the drain current changes with temperature. I'm going to write this and you tell me if I need to derive it again. It will be 1 over ID times del ID. I'm getting ahead of myself. It will be ID of T0 times 1 plus TCI times T minus T0. Do you all know where this came from? Or do I need to show the graph again? I need to show the graph again. So I get a TEMPCO, whatever it is, ID of T. And then at T0, we have ID of T0. And the slope of this is del ID del T. And we write that ID as this right here, and then that gives TCI equals 1 over ID times del ID del T. Just repeating like I did with the resistor. Any questions or comments about that? What's that? No. All right, let me go through this a little slower. So here, ID of T, I plot versus temperature, and I just drew it going down. It could go up, it could be flat. Then I say I'm going to measure the drain current in some room temperature, some temperature T0. I'm going to call that ID of T0. Then I know the slope of the line from freshman calculus is del ID del T. We all agree with that? Yes or no? Okay. So then I go back and I say, all right, well, I'm writing this equation, I0 T0 is 1 plus TCI T minus T0. So when T is T0, this term goes to 0, and ID is T0. When I take the derivative ID with respect to temperature, this goes away because the derivative of a constant 0. This becomes TCI, and this becomes just T, or del T, del T. And so this reduces to TCI times ID is the derivative of ID. Or TCI equals 1 over ID del T. Lots of letters, huh? All right, any questions about that? You want me to do it again? Yes?
What is TCI?
Temperature coefficient of the current. Let me do it one more time just to be super slow. Nice and clear, because I'm seeing confusion. I can tell. Okay, lab. I measure the drain current, ID of temperature, and I plot it. Let's go up this time. I want an equation for that current. If I ask, okay, what is the equation for the current? I go, oh, I measure the T at some T0. I measure the current, and that's ID of T0. I then say, okay, the slope of this line is equal to del ID of T del T. I'm going to write an equation for this line as ID of T is equal to ID of T0 times 1 plus the temperature coefficient of the current times T minus T0. So if I take the derivative of this, let's feel the pain. I got ID of T0 plus TCI times ID of T0 times T plus TCI times ID of T0 times T0. Which term there is not a constant? This I measured, it's a constant. This is just T0 times the measured term times TCI, which is a number. That's a constant. And this is not a constant, it changes with temperature. So then I say, oh, the derivative of ID with respect to temperature, knowing this term and this term go to 0, is equal to TCI times ID of T0 del T, which is 1. Or the temperature coefficient of the current is, moving this down, 1 over I. I'll just be sloppy and write ID like this. Any questions before we go back to our temperature behavior of the beta multiplier? So now, everybody understands? Okay, so now when I go back here and I write 1 over ID is equal to the temperature coefficient of the current source, and I divide this by ID, these cancel, and I get this is equal to TCI. We're almost there. Okay, so let's go back now, and I'm going to write that TCI. And we'll do a simulation example just to show you. Is TCI is equal to minus 2 times the temperature coefficient of the resistor. What did I replace 1 over R del T with? Temperature coefficient of the resistor. And then 1.5, 1 over Kp del T is minus 1.5 over T. And if I go back in the book, because you don't believe me, 1 over Kp del T is minus 1.5 over T. Looking good? All right, so let's put some numbers in there and show you that I'm not wasting your time and this is actually useful. See, in industry, temperature behavior is really important. You design stuff that only work at one temperature, that ain't good. Okay, so let's say that, for example, in our simulation, we'll say TCR is equal to 0.002 or 2000 ppm. And of course, this is per degree C or Kelvin. And then we'll say at T equals 300 degrees K that this would be plus. So I get my temperature coefficient is equal to minus 0.004 plus, and then 1.5 divided by 300, if I do the math right in my head, is 5,000 parts per million, or 0.005. And let me just pause and make sure that's right. CALCU. And it's Microsoft, so it's slow. And that's 1.5 divided by 300 equals, yay. All right, it's 5,000 or 0.005. And so the temperature coefficient is equal to 1,000 parts per million per degree C, or the current will be I of T0 times 1 plus 0.001 times T minus T naught. So what is the, if I look at this and I ask, what is the slope? Or first off, just one important thing to note here. Notice how the temperature coefficient is only that number at one temperature. It's at 300 degrees Kelvin. And if I change this temperature, the temperature coefficient is going to change as well. That's like small signal analysis. I do a small signal analysis at one DC operating point, but if I change the DC operating point, my small signal analysis is going to change and the parameters will shift a little bit. But you can do it at different temperatures and different places, but if it's linear, then this will work. Okay? Next thing. If I do the simulation and I look at this, how do I tell if my equation's correct? For example, if I take the derivative of I and I plot that, do I expect to see 1,000 parts per million? No, I expect to see 1,000 parts per million times the current. So if I see the current's 20 microamps, and I multiply times 0.001, I should see 20 nanoamps change would be the derivative per degree C. Does anybody follow that? So let's do this. So I have to make sure I put these parameters in, but let's do the simulation. And I can go over here, and I'm pretty sure I have a simulation in chapter 23. And let me just look and see what it is. And let me see, beta multiplier, temperature, behavior. Oh, this looks so familiar. Let's look at 2314. Yeah, let's look at. That's weird. I guess I just have the result 2314. Okay, so this one uses an amplifier here. Do you think that's going to matter? No, not really. The temperature will change the gain of the amplifier, but it really won't have much impact on the overall currents. It'll be set just by what we just derived. Now notice, and I've made this mistake lots of times, see this resistor? If I don't put the temperature coefficient in for that, if I don't put the TempCo in for the, let's do control. If I don't put the temperature coefficient in for the resistor, I'm not going to get the right answer. Does everybody follow that? So let's hit run. And then I've got several currents here. So what I'm going to do, and let me see if I'm smart enough to do this. I'm going to get rid of this. I'm going to change this to, see if I can do it. I always forget. I think I can do temp. Let's go 0 to 100 in a 1 increment step. And then let's hit run. And then let's plot the current that flows. Why am I concerned about current, not voltage? Here I'm plotting the voltage.
Oh, because the resistance is going to change. So.
Well, I use that as a current mirror, right? So in current mirrors, I care about how the current changes. I don't really care that the VGS and the VSG are changing. So if the VGS is 822 millivolts and it changes temperature and it's 850, I don't care. What I care about my biasing is how the current's changing. So let's go plot that current and let's get a positive current so it's going the right direction. And you see there's a little bit of a curvature. So the current's 16 micro, and so I would expect the derivative to be, if my calculation's correct, 1,000 times 16 micro. So let's see what we get. And what's the command for taking the derivative? D. And note here, what's the derivative look like? It's going to be down here at the lower temperatures. Nearly 0, but if you look here where around room temperature, you're going to see some variation. Let's see what we get. I can tell it's going to be pretty close based upon these numbers. Let's see what we get. So down here we calculated roughly 16, and you can see that it's off a little bit, but you can see we're in the ballpark. All right, any questions on this discussion before I do a couple more examples? Okay, I've got a comment. If you look at, actually I'll hold that comment for a moment. There's no questions on how to derive the temperature behavior. So, I mean, we spend this one lecture, maybe a little bit next time. What is it? Yeah, some more discussion next time. But I want to also do course projects on Wednesday so you can get going again. But in reality, temperature behavior is really important in practical designs. All right. Okay, so let's not save that. Let's do another circuit here. Does anybody remember how the diode voltage changes if we hold the current constant and change the temperature? Saul, do you remember? Minus 1.6 millivolts per degree C. Yeah, those students in my Circuits 2 class, man, they have serious phone addictions. All right, here we go. I'm going to do the following, and you're going to tell me how to analyze this circuit. First question, independent of temperature. How do I calculate the current that flows? And assume that two NMOS are the same size and the two PMOS are the same size. Read the book. Well, won't this force the same current through both sides? So if there's the same current, won't these have the same VGSs? Isn't this voltage the same between both NMOS? So won't these two voltages have to be the same? So what, if I call this voltage V diode, what's this voltage over here? So what's the current, I? Easy? Or would you be okay if I wrote V diode times R to the minus 1? Why'd I do that? Yeah, to do the temperature coefficient of the current. So then I'm going to write, you're all going to do it for me, TCI, or whoops, let's do this, del I del T is equal to, does the diode voltage change with temperature? Yeah. So it will be the derivative of the diode temperature with respect to temperature times R to the minus 1 plus minus 1 times R to the minus 2 V diode times right on. Anybody agree with that? So let me write that as 1 over I, so this is the temperature coefficient of the current, times del I del T is equal to, okay, I'm going to write this I down here as R over V diode times 1 over R del V diode del T plus, and I should put minus, let's just put minus, minus V diode over R squared del R del T. Anybody agree with that? And then I'm going to come back over here. Am I right? 1 over I del T is equal to, multiply through 1 over V diode del T minus, the V diodes cancel with the V diodes, R cancel, 1 over R del T. And if I look back in the book at the parasitic diode references right here, I see that the diode changed 1.6 millivolts. So I'm going to write this. So this again is the temperature coefficient of the current. I'm going to rewrite this as how about I write it as the following. Minus, and then whatever the temperature coefficient of the resistor is. Okay, so if I look at this, what can you tell me about the polarity of the temperature coefficient of the current? It's negative. So Saul, if I plot the temperature versus I of T, I get a curve that looks like this. All right? This is called complementary to absolute temperature, or CTAP. And that's a term of art that's used in engineering. When you say something is CTAT, that means that it has a negative temperature coefficient and it goes down with increasing temperature. All right, does everybody follow that? Any questions? You ready for another one? Does this make sense? It's going so well. All right, let's crazy it up. Let's do this one. You're going to tell me, you're going to help me do this. I'm not going to do it on my own, because when I do it, it looks easy. At least I think it looks easy. Does it look easy? Carlos, does it look easy? All right. Okay, so let's do the following. Is this bringing back nightmares for you?
Yeah.
What's that? 320? You didn't learn this in 320. I'm going to call this diode, and you would agree these are forward biased, right?
Yeah.
And I'm going to call this one V diode 2, and everybody would agree that the current splits through all of those. Would you agree from 320 that you can write the diode current is equal to IS e to the V diode over NVT, where N is the emission coefficient? That's basically to shift the curves so they match the measurements. And VT is KT over Q, which is the thermal voltage.
What is that? KT over what?
KT over Q. What is Q? I say it as if everybody knows. Charge, electron charge. Right? How's that Einstein's coffee? Not good enough, huh? Sleepy, 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 sleepy head. All right. What's that? V, you haven't seen this thermal voltage? Here? It's this, thermal voltage, V sub T. Wait, have you seen this before? If you haven't seen this before, I'm about to shed a few tears and...
At 320, it's 320.
yeah.
Yeah.
All right, so would everybody agree that V diode is equal to NVT times the natural log ID over IS? So I could write this as V diode 1, and then for V diode 2, well, wait a sec. K times IS, I have K diodes in parallel. Does everybody agree that that would increase the scale current because I have a bigger area, bigger cross-sectional view? So would everybody agree then that I could write V diode 2 is equal to NVT natural log ID over KIS, and that the current through both sides is the same? Don't get confused, even though the diode there's K of them in parallel, they have an effective scale current or saturation current that's K times larger. Because the current splits, what can I say about the relative value of VD2 versus VD1? Now, simple question. What can I say about the relative value of VD2 versus VD1? VD2 is going to be smaller because I got less current flowing in each diode, right? All right, so now, yay or nay? Wait a sec, does this confuse anybody? If I put K diodes in parallel, the current coming down here is going to split in between them and the voltage across them is going to be less. Does that challenge anybody? Brian, does that challenge you? Yes. All right. So that voltage is less than this one. So now here I ask the next question. How do I calculate the current? Well, would everybody agree they have to be the same? I'm forcing them to be the same with the current mirror up here. So how do I calculate ID? Well, let's ask simple questions. What's that voltage?
VGS1 plus VD1.
But what's this voltage knowing it's the same size as this one?
VD1.
VGS1.
So what is that voltage right there? And what is that voltage right there?
VD1 minus VD2.
What?
Yeah.
Yes?
Is it possible that diodes can turn off?
You need a startup circuit. But if your circuit started up, then no, you're going to have current flowing in each side. All right, proceed. All right, so what is ID? Don't all scream it at once. VD1 minus VD2 over R. Crazy.
Wow.
And wouldn't I be able to write that as NVT natural log ID over IS minus NVT natural log ID over KIS divided by R? Anybody agree with that? And refresh my memory, what's the natural log of A minus the natural log of B? All right.
Every once in a while, but doesn't happen often. But
That's high school level, isn't it?
high school. How many days in elementary?
All right. So if I do that, what do I end up getting? I end up getting NVT natural log of K over R. So if K was 8, what's the natural log of 8?
2.
Roughly 2. And what's VT at room temperature?
25 degrees.
25 millivolts or so. And if N is 1, so if N is 1, VT is 25 millivolts, K equals 8, and R equals 10K. Let's plug in the numbers. What is ID? See, 25 millivolts times 2 is 50 millivolts divided by 10K.
About 5 minutes.
So that would be 25, it would be 50 millivolts over 10K, which is
5 minutes.
5 microamps. Just as an example. Yay or nay? Anybody not follow that?
That's changing the drain current overall. Just because of the temperature. So instead of
No, we haven't done the temperature yet. We're just finding the drain current. I got to find the temperature next.
So with all those components now added,
It's
diodes. Typically our standard is 20 micron.
No, that's not a standard. That's the number we're using for examples. So here's my circuit. I'm just trying to find a drain current that flows in this circuit where I've got diodes over here, diodes over here. And you might be asking, why would you want to do that? We will see. Trust me. Wink, wink. I'm from the government. I'm here to help you. All right, so everybody is okay with that? All right. So does everybody know this equation is just to calculate the current that flows in the circuit? We haven't done anything with temperature yet. So let's write that down again, and we write NVT, or R to the minus 1, natural log of K. Does K change with temperature?
No.
It's the number of diodes, right? It doesn't change with temperature. So what I'm going to do is I'm going to write del ID, and I'm going to write that as N times the derivative of the temperature with respect to temperature, or VT with respect to temperature, times R to the minus 1 natural log of K. Plus, and is it called product rule or chain rule when you do this? Product rule, all right. It's been 37 years since I took Calc 1, so I got an excuse. All right. And then it will be equal to NVT times minus 1 R to the minus 2 del R del T times natural log of K. Anybody agree with that? So whoops, is anybody getting nervous because I didn't do that? So would everybody be okay if I wrote this as NVT over R natural log of K times, why did I do that? To get back to ID, so when I do the temp co, divide by ID, it cancels out. And when I pull that out, this term gives me 1 over VT del VT del T. Anybody agree with that? And then when I pull this term out, I get 1 over R del T. Yay or nay? You never had a class with so many derivatives in one lecture that wasn't a math class? This is a math class? I don't think so. Question?
I think that you put an extra.
Yeah, you did.
Where?
Oh, yeah, there's.
Oh.
Third line.
Should I carry like white out and so I have nice professional looking notes? All right. Remind me, what's VT?
Temperature and
So what is del VT del T? All right. And would everybody agree that's equal to? Or I guess you don't know. If you plug, what's K again? Boltzmann's constant. You guys get enough use of Boltzmann's constant?
No.
That's 0.085 millivolts per degree C. I know what you're thinking.
Wouldn't it be?
What? It doesn't matter, it's the same, because it's a slope. You could say Kelvin or whatever. Where is that? VT, where art thou, VT? Right there. And the units are a little crazy, 0.085 millivolts per degree C, because you could write it as 85 microvolts per degree C. So don't make a mistake with that. Does everybody see that? Any questions? Okay, so now before I we can plug in numbers, but I want you to make an observation about the polarity of the Tempco here.
It is positive.
It's positive, right?
Hold on, hold on.
Hold
That's a
on.
minus sign in the middle, isn't it?
Where?
Yeah, it's minus 1 over r, delta r over delta t. One line above 0.085 millivolts per 12 degrees Celsius, that's a minus sign.
It is a minus sign. So that means we could have positive Tempco or negative Tempco, but let me see if I made a mistake. I'm looking at the one on page 763. And well, let's fix this first because you're right. All right, so this is positive, and this is negative. So if this term is larger than this term, then the Tempco will be positive. And if this term is smaller than this term, the Tempco will be negative. And if I plot that current and it's got a positive, then this is proportional to absolute temperature. And that's called PTAT. And so I want to set the stage for next time when we come back, and I'll cover how to do the diodes and CMOS when we come back next time as well. But I want to set the stage here that if you take that current and, well, let me ask this. So let me write those equations down real quick. I guess we don't need to, they're in the notes. But if I take that circuit here, and everybody's cool if I just write K next to that. And I come over here. And I go, and I do the following. Oh, so let's see. We said the current flowing through here is NVT over R natural log of K. Correct? So now if I come over here, and I go to a resistor, and I take that resistor and I say this is V ref, and I ask you, this is where I cringe, let's call this R2, R1, R1, and I ask you, what is V ref?
IV times R2.
So what's this current? So would everybody agree then that V ref would be NVT R1, R2 over R1 times the natural log of K? Okay, so now if I ask you in this particular situation, assuming these resistors are made with the same material and thus have the same temperature coefficient, if I ask you what's the temperature behavior of that voltage reference, what's the answer? It's going to be the 85 millivolts term, right? Because what happens to the temperature behavior of the resistors? As they change with temperature, what happens?
Go.
They divide out. The changes divide out. So if they were the same size and they both go up by 100 ohms, then you still get the ratio of 1. If R2 was twice as big as R1, then R2 would go up by 200 ohms and R1 went up by 100, and you would still get a ratio of 2. So the resistor temp code divides out. And just so you understand that, or you agree with that, you could write these more precisely as R2 of T0 times 1 plus TCR times T minus T0. Notice the TCR is for the material. It's not for the particular value of resistor that you have. All over R1 of T0 times 1 plus TCR times T minus T0. And in that case, those divide out and you're just left with the resistor values. It doesn't change with temperature. Does everybody see that? So now if I ask, is this reference that I just designed, is that PTAT or CTAT? It's up, it's PTAT. So now, when we come back next time, we're going to use a band gap reference that takes a CTAT and a PTAT reference and combines them together to give a reference that doesn't change, ideally with temperature, and that's called a band gap. Now, why is it called a band gap? I'm sure everybody's anxiously reading the book, but when we come back, I'll try to remember to go over this first thing. The band gap energy of silicon will decrease with increasing temperature. And so we're using that fact with the diode to explain why the diode forward voltage drop is decreasing with increasing temperature, to design a reference which is independent of temperature, a band gap reference, okay? So just so you know what happens. So here you see we've got one diode, and I'm going to cover this later. These are diodes. Just think of them as exactly what we covered. Here's K diodes in parallel. Here's the resistor. So then there's your NKT over Q times R times, I separated it out. The KT over Q is the VT times the natural log of K. Then instead of setting it through just a resistor as I did right here, we're going to send it through a resistor and a diode, and then we're going to make this resistor have some value, and we're going to select this value to generate a reference voltage that doesn't change with temperature, that stays steady. And you should recognize, if you had 421, you should recognize this circuit from the circuit I had you lay out and use in your projects.
Yeah.
Right? And you understand why now a little better, why if you change VDD, it doesn't influence the currents or the temperature behavior, because as long as you have a large enough VDD here, you're not going to affect the operation of the circuit. You should also be able to answer why the VGSs and the VSGs changing with temperature doesn't change the currents in the circuit. Right? Because if it goes, the temperature change in threshold voltage goes from 800 millivolts to 750, who cares? Doesn't influence the current mirror action. All right, you ready for a quiz?
No.
All right, I take that as a yes.